This is 6.2 and it's on one-to-one functions and inverse functions. The definition of a one-to-one function. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x sub 1 and x sub 2 are two different inputs of a function f, then f is one-to-one if f of x sub 1 is not equal to f of x sub 2. Okay, so another way of thinking about this, the easiest way for me to think of it visually, because I'm a visual learner and I know a lot of you out there are visual learners as well, I always think of this. A one-to-one function passes both the vertical line test, and hopefully you all remember what the vertical line test is. We covered the vertical line test when we covered functions. So the reason that it doesn't mention it here in the textbook is because all of these are already determined to be functions, and the vertical line test basically determines if something is a function. So it passes both the vertical line test and the horizontal line test, which we are going to learn about in this section. So if it passes both of these tests, it's going to be a one-to-one function. This is easy to visualize because you can just easily graph something on your graphing calculator and look at it, and you can ask yourself, is it going to pass the vertical line test? Is it, can I draw vertical lines everywhere and every vertical line will only hit once and no more than once? And can I also draw horizontal lines everywhere and every horizontal line will hit no more than once everywhere I draw it, right? So that's the way I like to think about it. Another way to think about it, if this definition, if it just didn't make any sense, you can also think of it as a function is not one-to-one if two different outputs, I didn't mean that. Let's cross that out. Let's say I meant two different inputs correspond to the same output. Okay, and that might be an easier way for some of you guys to think about it if you want to. Like I said, the horizontal line test, which says if every horizontal line intersects the graph of a function f in at most one point, then f is one-to-one. That's the easiest way for visual learners, I think, to think about this. So let's say we have a function here, and this function is going to be an increasing function. Okay, I know it looks like it levels out over here, like horizontally, but it's increasing everywhere, all across its domain. So this is an increasing function, and let's just call it f of x. And we already know it's a function, so that means it has to pass the vertical line test. The question is, does it pass the horizontal line test? If I draw horizontal lines everywhere I want, every single horizontal line is only allowed to hit at most in one point. So that's it. As long as every single horizontal line I draw anywhere hits in at most just one point, right? As soon as it hits two or more, it's not considered a one-to-one function. So this first example that I drew here, yes, it does pass the vertical line test. Now, this second function, let's call this second function that I drew here g of x. And it's a parabola that opens upward. It definitely is a function because it passes the vertical line test. But if I draw a horizontal line right here, I can see that this horizontal line is going to hit in 2 points. That means it fails the horizontal line test. Therefore, even though this is a function, it is not a one-to-one function. Okay, so hopefully that kind of helps clarify a little bit about what is a one-to-one function and what is not a one-to-one function. All right, it's very important that your f of x sub 1 is not equal to your f of x sub 2. So in this case here, like these 2 points that I have here, let's say this point right here is x sub 1, and let's say this point right here is this value for x is x sub 2, then I can clearly see here that g of x sub 1 is equal to g of x sub 2 because They both lie on the same horizontal line. Therefore, it does not follow that definition of a one-to-one function. We also have a theorem down here that says a function that is increasing on an interval I is a one-to-one function on I. For example, this first function that I drew here in blue, f of x, this is an increasing function, and as long as it's increasing everywhere here on the interval or on all across its domain, for example, on this one that I did, it's going to be one-to-one. And this one that I drew here, let's call this one h of x. This one is decreasing everywhere all across its domain. So because it's decreasing here everywhere, I can see, yes, that this is going to be also a one-to-one function because I can draw also horizontal lines everywhere, and I can clearly see that each horizontal line will only hit once. So h of x is a one-to-one function. All right, let's go ahead and go on to this next example that we have here. No, let's talk a little bit more about this one before I move on. No, let's move on. Determine whether the function is one-to-one. I look at the x's. All the x's are different, and then I look at the y's. All of the y's are different. There are no two y's that are the same, which is my concern, right? If I'm already told I have a function, then my concern is really with I have two y's that are the same with different x values. Because these are all different, I can say this one is one-to-one. B, I look at all the x's. All of my x's here look like they're different. I've got a 1, I got a 2, I got a 3, I got a 4. And then if I look at my, I can already tell here we have an issue, the 8. I can already see we have two y's that have the same value of 8 with different x values. Therefore, different inputs are giving me the same output. Let's call this x sub 1, comma, f of x sub 1, and let's call this x sub 2, comma, f of x sub 2. Here, f of x sub 1 is equal to f of x sub 2. Not good. Does not follow the definition of one-to-one, right? These are not allowed to be equal to each other. Therefore, this is not one-to-one. Here we have a couple of graphs. Why don't we go ahead and call this first graph 2a, and we'll call the second graph 2b. So the easiest way to determine if you're given a graph, whether it's one-to-one, is to, and if you're already told it's a function, go ahead and just perform the horizontal line test. So if I draw horizontal lines everywhere, every horizontal line that I drew here only hits at most once. So this passes the horizontal line test. Therefore, I can say that this function is going to be one-to-one. Looking at the second function that I have here, it's a parabola that opens downward. If I draw a horizontal line, and I don't have to draw this many, I could have just drawn one horizontal line. As long as I draw one horizontal line that anywhere that hits more than once, I'm going to be able to say it's not one-to-one. I can see here by looking at any one of these horizontal lines that this definitely fails the horizontal line test. Therefore, this function is not one-to-one. So you can see one-to-one functions, being able to tell whether they're one-to-one. Hopefully that's not too bad. Definition of an inverse function. Suppose y equal to f of x is a one-to-one function. It has to be one-to-one. The correspondence from the range of f to the domain of f is called the inverse function of f. The symbol f inverse is used to denote the inverse function of f. In other words, if y is equal to f of x is a one-to-one function, then f has an inverse function, f inverse, and x is equal to f inverse y. So let's talk a little bit about this definition, because there was a lot going on here. Why don't we go ahead and start off here with this first, the second sentence. The correspondence from the range of f to the domain of f is called the inverse function of f. Well, let's review about relations. If you guys remember, a relation is a correspondence between two sets. And those two sets are going to represent basically the domain and the range. And when you're working with a relation, the domain is going to get mapped to the range. So it goes from the domain to the range, right? The domain's like our input, and then we get our output as our range. Notice that this one says the correspondence from the range of f to the domain. Notice the order from the range to the domain. What came first? This time they wrote the range first and then the domain. So when you're working with an inverse function, you're basically taking that original function, that whatever you took the inverse of, and it's like you're switching the domain and the range around. So once you're working with an inverse function, whatever the original function is, you're taking the range of the original function, and that's going to get mapped to the domain of that original function, which I'm calling f here. So when you're working with an inverse function, it's like the range of f becomes your input, and the domain of f becomes the output, right? In the inverse. Everything just gets switched. Your x and y's basically just get switched. All right, I'm going to go ahead and make a table of values here as an example. Let's call the x values here 1, 2, 3, and then f of 1 is 4, f of 2 is 5, f of 3 is 6. Now let's say I wanted to find these points that matched up with the inverse of this function. So we got x here and then f inverse of x over here. So now everything that had the y values is going to go down the x. 4, 5, 6. And f inverse of 4 is 1, f inverse of 5 is 2, f inverse of 6 is 3. Notice how the x and y values basically just got switched. That's what happens when you have an inverse function, okay? So that's the most basic, most important part to remember there. F inverse is the inverse of f. And when you see this -1, I know it looks like a -1 that's an exponent up here, and a lot of times people look at this and they confuse it with the exponent. This does not represent an exponent. This -1 that's next to the f, that is the way we refer to f inverse. That's the notation we use. So very, very important. Write this in your notes. This is not an exponent. I know what some of you are thinking. How am I supposed to know the difference? It all has to do with the context of the problem. What type of problem are you working with? And oftentimes when we're working with functions and inverses, you notice we use certain letters for those, right? F, G. So there are favorite letters that we have to talk about functions. So oftentimes when you see like an F raised to -1, you know, and once again, talking about the context of the problem, you'll know it's talking about an inverse function, not a -1 exponent. Right? So try to keep that in mind. The graph of a one-to-one function f and the graph of its inverse function f inverse are symmetric with respect to the line y equal to x. So this is very important to remember, and we're going to see this right now visually for those of you that are visual learners right here in this next example. The graph of a one-to-one function f is given. Draw the graph of the inverse function f inverse of x. Let's call this 3a and 3b, okay? What I'm going to do is I'm going to, I should say letter A, for 3a, I'm going to do a table, but I'm going to use the values that were already given to me inside the graph. This blue, I'll call it the blue function here, I'm going to refer to this as f of x. Why don't I write down the points that were given to me here in this table of values? So I had 2, 1/2, 1, 0, 0, comma, negative 1, negative 2, comma, negative 2. If I want to find the inverse, I can use these points to help me. All I have to do is switch the values. So now, instead of 2, I'm going to put 1/2, comma 2, 0, comma 1, negative 1, comma 0, negative 2, comma negative 2. I'm going to plot these points, and I'm going to try to replicate the mirror image of this function across the line of y equal to x, if that makes sense. So let's go ahead and plot these points down. Here's going to be one of our points. Here's another one. Let's go ahead and label this point. This is 1/2, comma 2. This is going to be 0, comma 1. This is going to be negative 1, comma 0. And then I'm not going to plot negative 2, negative 2 because it's already plotted because that's the same point from f of x. Let's connect our points. So how does that look? Does that look pretty good? I think that looks pretty good, right? Sort of. Oh, I'm such a perfectionist. I don't like it. Let me try one more time, see if I can make it look a little bit more like straighter line segments. How about that? I think it looks a little bit better. Okay, so this image, I'm going to call this the green function. Why don't I refer to this function here as f inverse of x? This function is the mirror image of f of x across the line y equal to x. Notice how y equal to x is a line of symmetry between the two functions that I have here. That's always going to happen when you have inverse functions. Now, for letter B, we have an issue here. We don't have any points. So what I'm going to do is I'm going to use the point where it's intersecting the y equal to x line because it was given to me. And I'm going to try to just mirror image this line across the y equal x line. And I'm going to get it to go through those points of intersection. It's not going to be perfect, but that's okay. What matters is that you're getting the idea that basically we're just taking the mirror image of the line across, of the function across the line y equal to x, right? So this one isn't perfect. I can already see I could have done a better job maybe, but hey, it is what it is. I'm not gonna dwell on it. I did my best. We're gonna just move on. Oh, that's my dog scratching at the door. She wants to come in. Let me just let her in real fast, okay? Here you go, Roxy. You wanna come in? Come on. All right, where was I? We were talking about verifying inverse functions. Verify the functions f and g. Verify that the functions f and g are inverses of each other by showing that f of g of x is equal to x and g of f of x is equal to x. Give any values of x that need to be excluded from the domain of f and the domain of g. So what we're going to do here is we're going to take basically our g of x first, and why don't we find the domain of it? They gave us the domain. They specified the domain for f of x right there next to it. But we don't have the domain for g of x. It's going to be the set of all x such that x has to be greater than or equal to 0, right? Because we have a square root there with a variable inside, and it's just an x. So if we set x greater than or equal to 0, this is what our domain is going to be. So now we're going to find f of g of x. So basically, I'm going to substitute g of x as my input function into the f of x function. This is this has to do with composition of functions. So this was from 6.1, composite functions. We talked about this already. So hopefully you guys remember how to do this. This is going to be the square root of x plus 2 minus 2, all quantity squared. And if we simplify this, the 2 and the negative 2 cancel out, and we're left with the square root of x squared, which is equal to x. That means that, yes, well, we only have done half of it. We still have to do the other half. We still are missing the g of f of x portion, right? Now, since g of x was the input, that's going to be what's going to determine our domain, or where we're going to come up with what are our restricted values, right? So g of x is the input. We're going to look at the domain of g of x. And I'm just going to write that over here to the side. And I normally like to write domains in set builder notation and interval notation, but this textbook likes to just write it out like this: x is greater than or equal to x is greater than or equal to 0. So I'm just going to go ahead and do that just in case that's the way it's written on your homework. I'm trying to be consistent with your textbook. But normally when we write a domain range, set builder notation or interval notation. All right, g of f of x. Now I'm going to substitute f of x into the g of x. Every time I see an x in g of x, I'm substituting that x minus 2 quantity squared. So it'll be the square root of x minus 2 quantity squared. And then outside the square root, plus 2. So if I take the square root of x minus 2 quantity squared, the square root and the square cancel out. And then here, x minus 2 plus 2, the minus 2 plus 2 cancels out. We're left with an x. I'm going to focus on the f of x to determine what is the domain, or what are the restricted values here. F of x is the input. That's going to determine what we write down for our domain here. So they told us already. They said x has to be greater than or equal to 2. So we're going to use whatever they told us was the domain for that function. So I'm going to write here, comma, x is greater than or equal to 2. Excellent. So I believe that's all they were asking for here. So I'm just going to write out a little sentence here saying that these are actually inverse functions of each other. How about that? So just to make it look nice. So why don't we go ahead and write here that f and g are actually inverses of each other, because we went through all the trouble of verifying it here with our work. All right, let's go on to number 5. For number 5, we've got f of x is equal to x minus 5 over 2x plus 3. Let's find the domain of that one first before I do the domain for g of x here. Domain for this has a variable in the denominator. I'm going to take my denominator expression, set it equal to 0, and solve it. I'm going to end up with x is equal to negative 3/2. In other words, that's my restricted value. So I'm going to say that the domain for f of x is going to be the set of all x such that x cannot equal negative 3/2. Okay, this is domain of f of x. Let's find the domain of g of x. So once again, to find the domain of g of x, I notice that I have a rational expression and I have a variable in my denominator. I'm going to take that expression that's in the denominator, set it equal to 0, and solve for x. So this is going to be negative 2x is equal to negative 1. Divide both sides by negative 2. We get x is equal to positive 1/2. That's my restricted value for my domain. So it's going to be the set of all x such that x cannot equal 1/2. There, we found our domain. Now, what do we need to do next? We need to verify, are these actually inverses of each other? In order to verify if two functions are inverses of each other, we need to find the composition of functions. So I'm going to have to find f of g of x and g of f of x. And both of those, once I find those two compositions, they should both be equal to x. Let's find f of g of x first. So this means g of x is my input function. I'm going to input 3x plus 5 over 1 minus 2x into every time I see an x in f of x. So it's going to go into this x in the numerator, into this x in the denominator. Let's do it. Let's see what we get. This problem's going to be a little bit more work, because we're going to end up with what's called a complex fraction. And we're going to have to simplify this. But thankfully, we already know how to simplify complex fractions, right? We better know how to do that, right? If we're doing these type of problems. I'm going to use a method for simplifying this complex fraction. I'm going to use the method where I multiply the numerator and the denominator of the big fraction by the LCD, right? The LCD of both the numerator and denominator in this case are both 1 minus 2x. So if I multiply the whole big numerator and the whole big denominator by that 1 minus 2x, it will get rid of my little fractions within the big fraction. So that's what we're going to do. I'm going to multiply by 1 minus 2x, 1 minus 2x. So we're going to distribute here, distribute, and I'm going to distribute here, distribute. Notice what happens when I multiply to that first rational expression in the numerator. Oh, that's Roxy. She's scratching at my door again. The 1 minus 2x's will cancel out, and I'll just be left with 3x plus 5. And then that minus 5 will be distributed to that 1 minus 2x. Okay? When I multiply in the denominator portion, the first part, the 1 minus 2x's will cancel out. And I'll just have to multiply that 1 minus 2x to that 3. All right, let's go ahead and simplify this out as much as we possibly can. So we're going to end up here with f of g of x is equal to, let's put a fraction bar here. Actually, that didn't work out too well for me. How about this? How about if I just make everything on top here smaller? I think that will work. Let's give it a try. Let's see how that works. Yeah, I think that looks pretty, I think it looks better. Let's just move this over here a little bit. Maybe we can make it a little smaller. Just trying to make space. It's all about the space. All right, so here we have 3x plus 5 minus 5. Oh, that was supposed to be a plus 5. What did I do? I'm going to catch it right now. Don't worry, you guys. I will catch it. I'll come back to it and I'll make it a plus 5. But in your notes, you better have written 3x plus 5 for those first two terms in the numerator. Okay, so here I come back to say, okay, I need to combine like terms. Oh, wait a minute, what's that? Ah, it's supposed to be a plus 5. There, I fixed it, so it's fixed. If I combine these two 5s, this positive 5 and this minus 5, they cancel out. And in the denominator, I'm going to be left with just the 13x in the numerator. And in the denominator, that 6x and that negative 6x will cancel out. And I'll just be left with 10 plus 3, which is 13. 13x divided by 13 is x, and that is exactly what I wanted. Now I'm not done, right? Because I still need to verify g of f of x. But before I do that, let's talk about what is the domain here for this. What are the restricted values? My input for this one was g of x. So we're going to focus on the g of x function to determine the domain for this. So, and it looks like g of x, here's the domain up here, I'm highlighting it in green. It was the set of all x such that x cannot equal 1/2. So I'm going to write x cannot equal 1/2. There we go. And I usually, like I said, I usually like to write set builder notation and interval notation, but I'm writing it this way because that's the way the textbook is writing these problems out, and I want to stay consistent just so that when you guys do your homework, you know, it looks similar to what I did here in the notes. And I don't throw you guys like totally off here. I'm just trying to make more space, trying to make it smaller here. Let's try to, oh no. Just trying to get rid of that parenthesis right there. Trying to fix it. I like my notes to look nice, so that way I can upload them so you guys have access to them, you know. That way they look nice. All right. Here is our domain. We got it written out. We got everything shown there. And basically this whole process is the answer. I know some of you guys are thinking, what do we box? What's our final answer? The whole process here is the answer because we're trying to verify if these are inverses, so you need to show the whole process. It's not just a box of final answer type of problem. Every type of math problem is a little bit different. This type of problem, you got to show the steps, okay? G of f of x. So g of f of x, I'm going to take f of x, and that's going to be my input function now. I'm going to input f of x every time I see an x into g of x. I know this looks like a big mess already up here. I apologize. I'm trying to make it look like it makes sense, but I know it looks like a mess. So this is going to go in place of x here. This is going to go in place of x right here. Let's go ahead and write this out so you can actually see what I'm talking about without looking at this mess up here. Okay, so I think I'm going to move this down a little bit right there. That looks good. So the first part of the g of x says 3x plus 5. So it's going to be 3 times f of x, which is x minus 5 over 2x plus 3, and then plus 5. All over g of x says 1 minus 2x, but instead of x, I'm going to write x minus 5 over 2x plus 3. Now, what do? I'm going to use that same technique I used from the last problem we did. Or, I'm sorry, from when we right up above, the multiplying by the LCD to the numerator and denominator, okay? So let's go ahead and do that. The LCD in this case is 2x plus 3. Let's distribute 2x plus 3. And it's like, the reason I'm doing this is like multiplying by 1, because I got 2x plus 3 over 2x plus 3. And we're going to distribute, and distribute here. When I multiply the 2x plus 3 to the numerator, it's going to cancel out with that 2x plus 3 over there on top, right? So let me just make this smaller because I'm running out of space. So here I got an arrow right there. Now it looks good. Excellent. All right, so when I multiply the 2x plus 3 to that first expression, the 2x plus 3s are going to cancel out, and all we're going to be left with is 3 times x minus 5. Good, good. Plus 5 times that 2x plus 3. In the denominator, the 2x plus 3 gets multiplied with the 1, so that stays the same, and then it cancels out with the second expression. So we'll just have that minus 2 times the quantity x minus 5. Now here, we're going to do a little bit of distributing as well to simplify this whole expression out. We're going to distribute 3, distribute 5, distribute negative 2. Yes. And let's go ahead and rewrite this out because it's starting to look a little, lots going on here. G of f of x is going to be equal to, let's do a fraction bar, 3x minus 15 plus 10x plus 15, 2x plus 3 minus 2x plus 10. Combine like terms. These 15s up here, this negative 15 and positive 15 cancel out. Let's combine these 2x's, 2x minus 2x, these cancel out. We're going to be left here with a 13x over 13. And the 13s are going to cancel out or divide out, and we'll be left with an x. And what's the domain, or what are the restricted values? F of x was the input, so that's what we're going to focus on. We're going to focus on the f of x. So what was the domain of f of x? Well, let's look at the domain of f of x, and let's find out. You could probably tell by looking at our work what the restrictions are, but let's just go back to my domain up here. I'm going to highlight it in blue so it really jumps out at you. The domain of f of x was the set of all x such that x cannot equal negative 3/2. So, therefore, we're going to write here x cannot equal negative 3/2. And once again, we're not going to box in a final answer because the final answer here is all of the work we did because they asked us to verify if these were actually inverses of each other. And in that case, the work is what's going to verify that they're inverses. All right, this next problem. The function f is 1 to 1. Find its inverse and find the domain and range of f and f inverse. All right. So let's start off with the domain of f before we get started with finding the inverse. The domain is going to be the set of all x such that x is an element of the set of real numbers, and the range is going to be the set of all y such that y is an element of the set of real numbers, right? And that's, you guys should remember this. The way we know domain and range, we only have to watch out for 3 things, right? For domain. Can't divide by 0, you can't have any negatives inside of an even root, and you can't take the logarithm of 0 or a negative number. Well, there is no variables in a denominator, there are no even roots, and there are no logarithms. So that's how I know that the domain's all real numbers. Okay, step 1 for finding the inverse. We're going to rewrite this f of x as y. So I'm going to write, instead of f of x, y equals x cubed plus 1. That's your step 1. See? Step 2, you see the x and the y? We're just going to interchange them or switch them. So that's going to be our step 2. I'm going to write interchange x and y. So x is going to equal y cubed plus 1. Now, step 3. You see the y here? Now you have to solve for y. Yay! So let's go ahead and do that. Let's solve for y. I'm going to subtract 1 from both sides of the equation. And then I'm going to have x minus 1 is equal to y cubed. I'm going to rewrite it so that the y is on the left, because when I'm solving for stuff, I like that whatever I'm solving for to be on the left-hand side. So y cubed is equal to x minus 1. And now I'm going to have to take the cube root of both sides. Why don't I rewrite this over here first? And then I'll take the cube root of y cubed and the cube root of x minus 1. And we'll be left with y is equal to the cube root of x minus 1. Step 4. Step 4 is going to be to just replace the y with a f inverse of x with the proper notation to show that we have found the inverse. So step 4, replace y with f inverse of x. So my final answer is going to be f inverse of x is equal to the cube root of x minus 1. All right, so I think we can go ahead and box that in because that was one of our final answers they were asking for, right? They were asking for the inverse of our function, and this is the inverse. How could you check your work? Doing the steps we did up above, or the last problems we did, where we found f, g of f of x and f of g of x. You find f of f inverse of x and f inverse of f of x, and they should come out to x. The domain and range of f inverse of x are going to be the set of all x such that x is an element of the set of real numbers, and the range is the set of all y such that y is an element of the set of real numbers. All right, so I found everything I think it was asking for. Let's go ahead and box everything it was asking for right here. So domain and range of both f and f inverse, and then we got f inverse right there. I'm going to go ahead and go to the graphing calculator here, and I'm going to plot these for you. Let's start off by plotting y is equal to x cubed plus 1. And then let's plot the inverse. The inverse was the cube root of x minus 1. So I'm going to need a cube root here. Where is the cube root again? Oh, you know what? Before I do that, no. What am I doing here? Yeah, no. I think I need to find the cube root. So cube root, I think, is under... Oh, that's not cube root. Cube root, I think, is under... Oh, yeah, I think it's under math. I forgot, but I remembered. Number 4, cube root, x minus 1. And then I'm also going to plot y equals x, because that's the line of symmetry. When I graph these, they should look symmetrical to that line. That looks pretty good. You know, sometimes I like to go to the square function for the window. So I'll go to number 5 under zoom. And that makes it square, so it looks a little bit more symmetrical. And that looks very nice. I like how that looks. Yes. So I'm going to go ahead and I think I'm going to put this graph right next to all the work. How about that? So I'm going to, in order to do that, I'm going to need my snipping tool. Let me find it real fast. And there you go. Isn't that nice? And that way, when I upload my notes, if you guys wanted to see the graph of it next to it, you can see the graph. This is, I know my visual learners really appreciate this kind of stuff, because my visual learners, they really associate well with, associating problems with pictures helps them remember stuff. And I know it would have helped me when I was learning this. So I do it for all those people that need to see those pictures. All right. Let's go ahead and go to the next problem here. The next problem is number 7. Number 7 says f of x is equal to x squared plus 9. But x has to be greater than or equal to 0. It's like they're giving us here a restriction on our domain, right? Why would they tell us this? I can tell by looking at this that there shouldn't be any restrictions on the domain. Why would they give me a restriction? Well, let me tell you why. This function is not a one-to-one function. If you guys can tell by looking at this, x squared, right? It's a quadratic. It's a parabola that opens up. So because it's not one-to-one, when you don't have a one-to-one function, you're not allowed to find the inverse. But if we were to restrict the domain, well, then that's a different story. With this restriction on the domain, that would make this a one-to-one function, and therefore that would allow us to be able to find its inverse function. Isn't that cool? Yeah, I know. You guys are pretty mesmerized by this, blown away, right? You're like, wow, yeah, I didn't know that. I'm going to go ahead and graph this to show you guys that this is actually a parabola. Oh, that's not a very good graph. Let's adjust our window. I'm going to make the the y max. When we go up higher, let's go to 20. Oh yeah, you see it there? It's a parabola. This is a function. It passes the vertical line test, but it does not pass the horizontal line test. Now, what if I put that restriction on the domain here? We'll put the division symbol, open up a set of parentheses, and put x has to be greater than or equal to 0. Ah, look at that. Look at what happened here. I now have a one-to-one function. Isn't that cool? Yes, it is. Yes, it's very cool. Yes. So now, knowing this, I can totally work with this function. I can totally find the inverse of this particular function here, and I can get the inverse function, right? Let's go back. First step, replace f of x with a y. Second step, interchange x and y. Third step, solve for y. Now, when you solve for y, look at what happens here. If I take the square root of both sides, I got to include a plus or minus. So this is going to give me y is equal to plus or minus the square root of x minus 9. Now, there we have an issue here. We have to ask ourselves, do we really need both of these equations? One of these equations is going to be y equals negative square root of x minus 9, and the other one is y equal to positive square root of x minus 9, right? But are these both actually the inverse function of the one that we're looking for? We should check both of these. Let's check them on the graphing calculator. What do you think about that? If I go on ahead and plug them into the graphing calculator and look at the graphs, that should be able to tell me by looking at it visually which one is actually the inverse function. Let's go to y equals. Let's go to y sub 2. I'm going to go ahead and put for y sub 2, I'm going to say it's equal to x, because I like to put my line of symmetry there to see where it's supposed to be reflected across. Y sub 3 is going to be my positive square root of x minus 9. Y sub 4 is going to be my negative square root of x minus 9. Now let's go ahead and graph this and see what we get. So I can tell that one of these works and one of them doesn't. Can you guys tell which one works and which one doesn't? Look at the light blue one. That's the one that's going to be the inverse. The pink one is not the reflection of our original function across that y equal to x. Another option would be, if you can't tell by looking at the graph, is maybe using your table of values. You know, but we got a lot of numbers going on here. This might be more confusing than it's worth. But like, look at here with the y sub 3 and the y sub 4, I've got, what do I got? I got the x equal to 9 and then y sub 3 and y sub 4 equal to 0, so that's not going to work. What if we look at the 10? 10 is equal to, y sub 3 is equal to 1 and y sub 4 is equal to negative 1. So if we were to interchange those, the one that has the interchanged values for the y sub 1 is going to be our answer. Oh, look, 1, 10. That's going to be the one that matches up, right? We had 10, 1 for the y sub 3, and then 10, negative 1 for the y sub 4. And the only point that had the interchanged values for the y sub 1 would have been that 10, 1, because when you come up here, all of those are error up there, but when you come down here to x equal to 1, we got 1, 10, right? There is no negative 1, 10. It says negative 1, error. So the only one that works is the 1, 10, which is associated with the y sub 3, that light blue graph. So let's turn off the y sub 4. And now let's look at this again. Ah, yes, much better. Yes, that's it. That's our answer, right? That's going to be the one we want. Let me see if I could try to square it. Let me press 5. Oh, that doesn't look good at all. No. So I messed up my window here. But you guys already, I think I showed enough for you guys to see that that was the answer. Let me go ahead and copy the graph that I have over here, the littler graph, the smaller graph that was saved on the side. I'm going to copy that to put it on the notes. If anybody wants to see it later on once I upload the notes. And I'm going to go here, copy and paste. And we'll just attach it right about here. Let's see if I can make it right there. That looks good. Okay, I think we're ready to go on to the next problem. I know I already worked out the problem ahead of time, right? I'm doing the calculator part afterwards, but can't be perfect, can't do everything perfectly, right? Okay, I'm going to cross out that y equal to the negative square root of x minus 1, and the only one I care about is the y equal to the positive square root of x minus 1, but we have to still rewrite this with the correct notation. F inverse of x is equal to the square root of x minus 9. That's what we're going to box in. Okay? Now, I need to know the domain. I'm going to set my domain greater than or equal to 0 and solve for x. X has to be greater than or equal to 9. So my domain and my range, and the range, remember, if you guys remember by looking at the graph what our range was, hopefully. So our domain is x is going to be the set of all x such that x is greater than or equal to 9, and the range is the set of all y such that y is greater than or equal to 0. Another option for getting the range is by looking at what was your original domain of your function, because remember, you're ultimately just interchanging the domain and range, right, when it comes to your inverse functions, right? So when I'm looking at this, domain and range of my inverse, I know that the original function has to have these switched, right? So my original function, what did my original function say? My original function domain said it was the set of all x such that x is greater than or equal to 0. And the range, if you remember by looking at our graph, it was the set of all y such that y is greater than or equal to 9, right? And if you wanted to look at what we had written down for our inverse, you could do that as well. Why don't I go ahead and let me move this 1 to 1 here so it's over here to the side. It's not boxed in. I don't want you to think that's part of the answer. But why don't I also go ahead and highlight the similarities between the domain and ranges here of the inverse functions. Here's the domain for f of x. Here's the range for f inverse of x. Here's the range for f of x. Here is the domain of f inverse of x. Notice how these values got interchanged for our domains and our ranges of these inverse functions. Let's go to number 8. Number 8 is f of x is equal to 2x minus 3 over x plus 4. So why don't we start off by finding the domain and the range. Domain. In order to find the domain, I'm going to take what I have in my denominator and set it equal to 0 and solve to find what are my restricted values on our domain. So I get x is equal to -4, but what that really means is that means x cannot equal -4, otherwise it's undefined. Good. The range for this, I think the range for this, the easiest way to do this is to do it on the graphing calculator. Just go to the graphing calculator and try to figure it out by looking at the graphing calculator. It's probably the quickest way to get the range for, especially if you have a rational function like this one. So I'm going to type this into the calculator, and this is going to come out to this. Okay, so it looks like I can definitely see where the vertical asymptote is supposed to be here, but there might also be a horizontal asymptote, right? So the question is, if there is a horizontal asymptote, which it looks like there is, if I look at the table of values, I got -4 comma error for the y, right, at -4. Oh, sorry, that's the vertical one, right? That's the vertical asymptote. I meant it looks like there is a horizontal one, but I might not be able to get that from the table of values. We might have to do this algebraically, right? The question is, if there is a horizontal asymptote, is the function crossing it? Because functions can cross horizontal asymptotes if you have one. Let's look at these leading coefficients of the numerator and denominator, right? If they're written in descending order, I'm going to have 2x over x, which is going to reduce to 2. So my horizontal asymptote is at y equal to 2. Now I'm going to set the function equal to 2 to see if there is a point of intersection between that horizontal asymptote and the function. Multiply everything by the LCD. That's going to give me 2x minus 3 is equal to 2 times the quantity x plus 4. So now I'm going to distribute the 2, and if I subtract 2x to both sides, I'm left with a negative 3 is equal to 8. That's a false statement. That means there is no solution to this equation. What does that mean? That means that the function does not intersect the horizontal asymptote. Therefore, my range is going to be the set of all y such that y cannot equal 2. Right? I can tell by looking at the function, there's nothing else going on, like there's no common factors, so there's not going to be any holes or anything like that. And yeah, so we're good here. Now, let's go ahead and find this inverse. Replace f of x with y. Interchange the x and the y. Now solve for y. Multiply through by the LCD. I'm going to get x times the quantity y plus 4 is equal to 2y minus 3. Distribute your x. We're going to get xy plus 4x is equal to 4y minus 3. Let's get all of the y's to one side of the equal sign, and then all of the other terms to the other side that don't have a y. So we're going to be left here with a xy minus 2y is equal to negative 4x minus 3. Let's factor out a y, but I'm going to need some more space. How about I insert some more space in here first? Now let's factor out a y. So y times the quantity x minus 2 is equal to negative 4x minus 3. Divide both sides by x minus 2. And now I'm left with y is equal to negative 4x minus 3 over x minus 2. Now you guys know, I've talked about this before in my classes, there is more than one right way to write this rational function, right? So let's talk about the different ways we can write this. I could factor out the negative from the numerator and write it like this for my f inverse of x. I can multiply that negative to the denominator and distribute it if I wanted to. I can also switch the terms in the denominator and write maybe 2 minus x like this. So what I'm trying to say is there's more than one right way to write this function. Okay, when you look at your examples in your textbook or on my math lab, keep that in mind. Okay? And I know some of you guys are thinking, wait a minute, there's an x minus 2 and a 2 minus x. How do I know which one to use to find the domain, Professor Olivas? And I would say it doesn't matter which one you use. If you did it correctly, they both have to come out to the same restricted value when you set it equal to 0. So we get x equal to 2 for both of them. So my domain, my restricted value for my domain for my f inverse function is going to be 2. And notice, I'm boxing in the domain and the range for the function. That was the restricted value for the range. That would make sense, right? That for f inverse, the domain is going to be the set of all x such that x cannot equal 2. You better get the same restricted value that you got for your range for the original function if you did this correctly. Now let's see here if I get the same value for my horizontal asymptote. So whether I take this function here at the front that I have written here at the front or the back, negative 4x over x is going to give me negative 4. So my horizontal asymptote is going to be at y equal to negative 4. So for my inverse function, it looks like the restricted value for my range is going to be y cannot equal negative 4, right? And if you still need to prove to yourself that there is going to be no point of intersection between the function and the horizontal asymptote, then what you would want to do, and I'm sorry, I may have made a mistake there, I fixed it now though, right? what you want to do here is you're going to want to set your function equal to the -4, solve that equation, and as soon as you get to a point where you can see that there is going to be no solution for this equation, you can stop. Right here I can already tell that I've got 4x on the left, I got 4x on the right. These are going to cancel out, and I'm going to be left with a false statement. There is no solution to this equation. Therefore, there is no point of intersection between my horizontal asymptote and my function, my inverse function. So I know that y equal to -4 is going to be a restricted value for my inverse function. So when I write out my range, I'm going to write the range as range is equal to the set of all y such that y cannot equal -4. Okay? So hopefully that helps out with that problem. Maybe we should go to our graphing calculator also to go ahead and see this so that I can prove it to you by looking at the graphing calculator. Maybe that might help as well, right? First, let me write down the range. And let me go ahead and box that in while I'm at it. And that looks pretty good. And once again, notice the domain for our regular function had the same restricted value as we had for the range for our inverse. And the range for our regular function had the same restricted value as we did for the domain of our inverse function. And let me go ahead and box the inverse function, because that's what the problem was asking for. And here it is. It doesn't matter which one you would have used of these, different rational expressions that I wrote down here afterwards. I just chose the first one. Let's go into our graphing calculator. Why don't we go ahead and y sub 2, I'm going to put in my axis of symmetry, which is going to be y equal to x. Y sub 3, that's going to be my inverse function, which is going to be that -4x minus 3 over x minus 2. Let's graph it. Okay, so that looks all right. Let me try that square, that zoom square. So number 5 on zoom. So number 5 says z square, press 5, and hopefully it will square out this graph a little bit more. Yes, that looks a little nicer, a little more even. You can see the symmetry between that y equal x line. So hopefully this helps solidify that idea that these truly are inverses of each other and what it means to be inverses of each other. I can't emphasize enough how important it is for you to, really look at this and understand this, to really feel like comfortable working with all of these different functions, working with finding the inverses, working with composition of functions, really feeling comfortable with that, especially if you're going to go on to higher level math. So you don't want to take this class and you don't want to just say, oh, I kind of understand what's going on. I think I'll sort of pass this class, like barely. You don't want that. You want to make sure that you are understanding this class and you have a strong foundation on these topics. And when you are working with all these different functions and finding inverses and finding the domains and the ranges, you are feeling very comfortable and very confident in doing these things. All right? I just can't emphasize that enough. Okay, so good job. You made it to the end of these notes. I'm very proud of you. Yes, high five. Keep up the good work. And until the next section, I'll see you or talk to you again. Bye-bye.